Okay, in this video we're going to start section 6.2, differential equations, growth and decay. And in this section we're going to use a separation of variables to solve a simple differential equation. And then we'll use exponential functions to model growth and decay in applied problems. So in the last section, we learned to analyze visually the solutions of differential equations using slope fields. Analytically, we've learned to solve only two types of differential equations. Those in the form of y prime equals f of x and y double prime equals f of x. In this section, you're going to learn how to solve a more general type of differential equation. The strategy is to rewrite the equation so that each variable occurs only on one side of the equation. Separate your x's and your y's. This strategy is called separation of variables. And we're going to get deeper into detail in this strategy in the next section, 6.3. But first let's check out here example 1. This is a simple differential equation and it's y prime equals 2x over y. Now if you open your textbook to example 1, you'll see this solved in a slightly different manner than the way I'm about to do it. I don't like this prime notation. I think it's easier to see what's going on with the Leibniz notation. So I'm going to rewrite y prime as dy dx, and that's equal to 2x divided by y. And the idea is to separate the variables. X is on the one side, y is on the other side. So let's see here. We could multiply both sides by y and multiply both sides by dx, which you can see is just the idea of cross multiplication. If I cross multiply here, I'm going to have on the left side y times dy equal to, on the right side, 2x dx. So I've separated my variables. Y and dy are on the left, x and dx are on the right. And now I can integrate both sides of the equation. So on the left here I'm integrating with respect to y, so this becomes 1/2 y squared plus c. And that's equal to, raise the exponent by 1, divide by that exponent, and we'll cancel the 2. Over here we're going to have an x squared plus c. Could we just subtract c from this side? And let's even call this, this would be c sub 1 and c sub 2. They are different constants. We don't know what they are. If I subtract c1 from this side and from the other side, c1, one arbitrary constant minus another arbitrary constant is just a third arbitrary constant. So I'm going to have 1/2 y squared equals x squared plus, and we could just call it c sub 3. Or let's just call it c, because that's where we're going to leave it there. Let's subtract x squared from both sides. So now on the left I'll have 1/2 y squared minus x squared equals our arbitrary constant. And I'm going to multiply through by a 2. So on the left I'm going to have y squared minus 2x squared equals, and an arbitrary constant times 2 is still just an arbitrary constant. And we can leave our final answer just like that. Y squared minus 2x squared is equal to c. Again, the book does it in a slightly different notation with the prime notation. Eventually it gets to the point right around here where the methods do match up. I think it's a little harder to get there instead of just changing that y prime into dy dx with the Leibniz notation. And this sort of explains what I did with the constants. Note, when you integrate both sides of the equation, you don't need to add a constant of integration to both sides. What we could have done is, back here, when I integrated both sides, instead of putting this here at all, I could have just said we're going to add one arbitrary constant to one side of the equation and leave it at that. Because here's what we did. I like to work through it step by step. We subtract one constant from each side. Those just turn into, again, yet another arbitrary constant. Now, growth and decay models. In many applications, the rate of change of the variable y is proportional to the value of y itself. If y is a function of time t, the proportion can be written as follows. dy dt equals k times y. The rate of change of y, dy dt, remember the derivative is a slope or a rate of change, translates to equal, this rate of change is proportional to y. And the general solution of this differential equation is given in our following theorem. if y is differentiable function of t such that y is positive, and the derivative y prime is equal to ky for some constant k, then we have y is equal to c, some constant, times the exponential base e raised to the power kt, where k is that constant of proportion. C is the initial value of y, and k is the proportionality constant. Exponential growth occurs when that exponent, k, is positive. Exponential decay occurs when k is negative. And if we want to think about that graphically, let's see here. So we have this function ce to the kt. If this is positive, if k is a positive number, if k is greater than 0, it's an exponential growth model. And you know, the graph would generally be shaped like this, exponential growth. If k is negative, if this exponent up here has a negative sign in front of it, that would be an exponential decay, and we would be coming down and approaching the x-axis. And I did forget to mention here. So, all solutions of y prime equals k times y are of the form y equals c e to the kt power. Remember that you can differentiate the function y equals c e to the kt with respect to t to verify that the derivative y prime is equal to k times y, the proportionality constant times y. So here in example 2, we are going to use an exponential growth model. So it says here the rate of change of y is proportional to y. And when t is equal to 0, y is equal to 2. And when t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? So we know that the rate of change of y is proportional to y. And here are some initial conditions. 0, 2 is a point on the graph. And we see that here graphically. And when t is 2, y is 4. That's another point, another initial condition, 2, 4. We want to find the value of y when t is equal to 3. So when t is 3, you know, what is our y value? And because y prime equals ky, y prime equals ky, y and t in this problem are going to be related by our equation y equals c e raised to the kt power. Because it said here the rate of change of y is proportional to y, so we know that this theorem is going to apply. So we start with our initial condition. And I'll write that. We begin with the initial condition. And we're going to start with 0, 2. When t is 0, y is 2. So we're going to plug that into this equation. Our y value is 2, and that is equal to c e to the k times 0. Our numerator is 0 times k. And 0 times anything is 0. And e to the 0 power, or anything to the 0 power, is equal to 1. This becomes 2 is equal to c. So now we're going to use that again in this equation. And let me rewrite it. Y equals, now it's not c, because we found c was equal to 2 e to the kt. Get this out of here. So we used our first initial condition, 0, 2, and we found a value for c. Now we're going to use this equation, let me rewrite it up here, with initial condition. Our next initial condition was 2, 4. So when we plug these values in, our y value is 4. That's equal to 2 times e, and now we have our t value is a 2, so now our exponent is 2k. Okay, now we want to solve for k. and it's stuck up here as an exponent above our base e. How are we going to get that down so we can solve for it? What do we do to get rid of the exponential base? Let's see, the first thing I'm going to do here is divide by 2. So that's going to be 2 equals e to the 2k. Now, to get rid of that base e, I can take the natural log of both sides. I'm going to ln the 2, and I'm going to ln this side, and the ln of base e cancel each other out. So now on the left is the natural log of 2 is equal to, this exponent drops down and becomes 2k. And so to solve for k, we would divide by 2. K equals the ln of 2 over 2, or half the natural log of 2. And let's get that down to 4 decimals. We'll take that as approximately 0.3466. So let's see, I'll clear a little space here. We've found everything we needed. Back from our original equation, first we solved for c, and we found that was a 2. Y equals 2e. And then we had kt. Down here we solved for k. So that exponent is 0.3466 times t. And you know, that shows us our y value when, or no, that isn't our y. We'd have to stick that into the equation to find our y value. The original equation is, what is the value of y when t is equal to 3? So we would just punch this into our calculator, 2e, and our power is 0.3466 times t. T is 3. And when we evaluate this expression, we get a value of 5.657. So when t is equal to 3, the y output is going to be 5.657. Radioactive decay is measured in terms of half-life, the number of years required for half of the atoms in a sample of radioactive material to decay away. The rate of decay is proportional to the amount present. The half-lives of some of the common radioactive isotopes are shown below. Uranium, over 4 billion years. Plutonium, 24,100 years. And then carbon, radium, Einsteinium, nobelium down to 25 seconds. So here in example 3, we're going to suppose that 10 grams of plutonium isotope, 239Pu, was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay down to a single gram? Okay. So let's see here. It says we know that this is a proportional relationship. So we know that we're going to use our equation, y equals c e raised to the kt power. And let's see, we have an initial condition. When we start at time 0, we have 10 grams, and let's use y to equal our mass of plutonium in grams. So at time 0, we have 10 grams, or we have an initial condition of 0, 10. Okay, at what point will we know that we have half of this? You know, we have that half-life. So how long does it take our sample to go from 10 grams down to 5 grams? Well, plutonium has a half-life of 24,100 years. So the time is going to be 24,100, or that is our other point on the curve. 24,100, 5. Okay, we're going to start with this equation and our first time 0 initial condition. So at time 0, our y value is 10, and that becomes CE raised to the 0 times anything is 0, so this is e to the 0 power. E to the 0 is 1, so that just becomes C is equal to 10. And we plug that into our formula. Y equals 10, e to the kt. Now we use our second initial condition. The time 24,100, y is equal to 5. So y is equal to 5, and then we have 10e raised to the 24,100k. So let's see, divide both sides by 10, and over on the left side we're going to get a half equals e raised to 24,100k power. And then here's where we take the log of both sides. We'll take the ln of the left and get the natural log of a half, and that's equal to the natural log. Here we'll wipe out the exponential base, 24,100k. So we divide by 24,100, the natural log, or the log of a half, divided by that 24,100, and we're going to get k as approximately negative 0.400000 28761. 28761. So there's our final equation. Y equals 10e raised to the power negative 0.0000 28761 t. So there's our model, our equation, and now we can actually get around to answering the question that was asked, which was how long will it take to get for the 10 grams to decay down to a single gram. So we're solving for t, and if we went from 10 grams down to a gram, that's our y value. Our y value is 1 gram, and we want to solve that for 10e to the negative 0.000 28761 t. We want to solve for t. So divide by 10, and we're going to get 1/10 is equal to e to that power, and then we natural log each side. The natural log of 1/10, or 0.1, is equal to the natural log, of course, takes care of the base e, negative 0.000028761 t, and then we divide by that big negative decimal. And when you punch that into your handy calculator, you're going to get t is approximately 80,059 years. Okay, and that's a good place to end this video. In the next one, we'll get into some better and more real-world examples. This radioactive decay one was pretty good. In the next video, we'll do a population growth model, a declining sales in the business world model, and we'll talk about Newton's law of cooling.